Okay, so at the end of the last video, we talked about how with different t-distributions, t-distributions, they're going to look different for each sample size. So the standard normal curve, the z-distribution, always looks about exactly the same. Okay, so it says that the z-score within 2 standard deviations away from the mean, you're going to have 95% of your data. That z-score is negative 1.96 and positive 1.96 for your critical z-scores. Now, with the t-distribution, for each sample size. So that means when I take a sampling distribution where each of these sample sizes are 3 and then take the mean, put that on there. If I take a sampling distribution where I'm looking at samples of size 50, the t-distribution is going to change. So that's why we specify the t-distribution by the degrees of freedom, which is n minus 1 or the sample size minus 1, because the t-distribution, the amount of area in the tails, changes depending upon the sample size that you take for each of your sampling distributions. And we'll go over what that looks like. So when we compare the density curves, so we're going to compare the density curve to the standard normal curve and to the t-distributions just to see what they look like. All right, so take a look at this purple curve right here. This is your standard normal distribution. Okay, so the purple curve is my standard normal curve. Now notice the red curve is my t-distribution with 2 degrees of freedom. That means each of the samples in the sampling distribution were size 3. Now notice it's not quite as high as the normal distribution, and notice how there's more area in the tails. Notice how the green curve has 9 degrees of freedom. All right, it has a little bit more area in the tails, but not quite as much as the red curve, and it's a little bit closer to the peak of the normal curve. T-distributions have more areas in the curve or in the tails, which is this portion of the curve, than the standard normal curve. Okay, and 9 degrees of freedom means that there were samples of size 10. All right, so let's just talk about the two together. So the density curves of the t-distribution are similar in shape, so they have about the same shape. We just said that there's a little bit more area in the curve with the t-distributions than with the normal curve. Now, what does that mean about the spread? That means since there's more area in the curves, the spread of the distribution is going to be a little bit bigger than that of the normal distributions. They have much more probability in the tails and less in the center since they're not as high than the standard normal distribution. As the degrees of freedom increase, so as you choose larger and larger samples for your sampling distribution, if you notice this was 2 degrees of freedom versus 9 degrees of freedom, the t-density curve looks more and more like the standard normal curve. Okay, so what does that allow us to do? So when we perform inference about a population mean mu using a t-distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size. So you always want to state your degrees of freedom when you are talking about a t-distribution, because that's going to tell us how close it is to the normal curve. Like I said, because every t-distribution is going to look different depending upon the sample size. So your t-distribution, and when I say look different, it also means it's going to have different areas in the curve. So if you take a look at this green curve and you're finding the area from here to here, okay, it's going to have less area in the tails than if I'm using the red curve, okay, because this red curve has more area in the tails, less area up here. All right, so the areas are going to change depending upon what t curve you use. So you always want to make sure you include the degrees of freedom. Okay, now the t-statistic literally looks exactly the same as the z-statistic. The only thing that we don't know is the only thing that's different is we're using the sample standard deviation instead of the population standard deviation. So to get a t-score, we're just going to take your sample mean minus the population mean divided by the sample standard deviation over the square root of n, because this is using the sampling distribution where we're taking samples of size 5, 10, whatever. Okay, now when the population distribution isn't normal, the statistic will have approximately t n minus 1 distribution if the sample size is large enough. Okay, so basically what this is saying is if we have a population distribution that is not normal, then it's going to follow a t-distribution based on the degrees of freedom which would be based on the sample size that you choose, okay? And then we say if the sample size is large enough, so once we get to this, we're still going to be talking about the central limit theorem again. Okay, so how do I find critical t-values if every single solitary curve is different? Well, it's actually pretty easy. It's the same that you did with your normal curve. You're just going to tell your calculator, hey, we now have different t-curves, so you have to tell your calculator what degrees of freedom or what t-curve to actually look like. So suppose you want to construct a 95% confidence interval for a mean mu of a normal population, so we know the population is normal, based on a simple random sample of size 12. So what critical t should you use? So number one, you know you have a 95% confidence interval. The degrees of freedom is 11 because the sample size was 12, so 12 minus 1 gives me 11. Now you're going to do it the exact same way that we did with the standard normal curve. Think about this, inverse t, okay, instead of inverse norm, because we're not looking at a normal curve, we're looking at an inverse t curve. You're going to put the percent under the curve to the left, and now you're just going to put the degrees of freedom. So in this case, you're going to do inverse t 0.025. That would be to the left of the first critical z-score, 11, which gives me negative 2.2, or inverse t 0.975, that would be your upper bound critical t-score, with the degrees of freedom 11, which is 2.2. So our critical t-score in this case is 2.2. Now, think about that. If we had a 95% confidence interval, your critical t-score would have been, or your critical z-score would have been 1.96. So this is saying that this critical t-score, there's more area under the curve, all right, because you're going from negative 2.2 to 2.2 standard deviations, where with the z-score, you would have only been going from negative 1.96 to 1.96. So this actually captures more, the t-distribution is actually capturing more sort of area under the curve. Okay, so what critical t-value? So sometimes you can use it from a table. So there is a table in your notes. Sometimes it's easier to find it from your notes than it is from a calculator. So what critical t-value from table B, and I know this is table B, but yours is just a table that's in this section, should be used in constructing a confidence interval for the population mean in each of the following settings. So we want to take a look at a 95% confidence interval based on a simple random sample of size 12. So this is the same as the last section. So here's how you're going to do this. So in the table, all right, notice how this says upper tail probability P. First thing you're going to do is you're going to find the degrees of freedom, 12 minus 1, which is 11, right here. So now we know it's going to be somewhere in this row. How do we know what column to use? This says upper tail probability P. So this is where it's actually going to be important, I think, to draw your curve, all right? So if we draw this curve, we know we have a 95% probability. So here's our 95% confidence interval. Okay, we know that this is going to be 0.25 or 2.5%, and the lower tail probability is going to be 0.25 or 2.5%. So what we're going to do is we're going to use this upper tail probability to find what our critical t-score is going to be. So the degree of freedom part is easy. So we're just going to look at what is the upper tail probability, what is above sort of this z-score right here is 0.025. Okay, and then we just find the intersection, 2.201, which is the exact same thing that you got from your graphing calculator. Okay, so what critical t-value from table B should be used in the following situation? We now have a 90% confidence interval with a sample of 48 observations. All right, so with 48 observations, we know that the degrees of freedom should be 47 and a 90% level of confidence. Well, if you start taking a look at your table, after you hit a certain point, it doesn't do 31, 32, 33, 34, 35. Okay, if you have a degrees of freedom of 47 and it's not on there, you always go down to the nearest row below it, okay? So there's no 47, so drop down to the next lowest, which would be 40. All right, now think about what the upper tail probability is with 90%. You have 90% in the middle. That means you're going to have 5% above and 5% below. So the upper tail probability is 0.05. So take a look at that intersection as 1.684. Okay, now we could do it with calculator commands. You could do inverse t of 0.95. Okay, now remember, so here's sort of the difference here. On your graphing calculator, it's always the area to the left. So the same thing that you do with inverse norm. Since it's always the area to the left, it's 0.95. And then we're going to use the degrees of freedom of 46, 1.67. So very similar values. But the table gives the upper tail probability. So just know the difference between the two. Okay, so same thing with proportions and with sample means. You're going to have to check some conditions before you use a t-distribution. All right, so same thing that we talked about before. You still have to be a simple random sample or else we can't make inferences about the population. We still have to prove our independence, so that's the population being 10 times the sample size, and that's for that standard deviation because we're still dividing by the square root of n. Then the approximately normal distribution is a little bit different. Number one, if the population is normally distributed, then we can say that the t-distribution is normally distributed. All right, if we don't know what the population is, if the sample size is large enough, n is greater than or equal to 30, then it's approximately normal by the central limit theorem. Now, if the population distribution is unknown and n is less than 30, we can still prove it's normal by two different ways. You can either use a normal probability plot or a box and whisker plot. So what you would do is you would create a normal probability plot on your graphing calculator. Remember, if a normal probability plot is linear, then your graph's approximately normal. You would have to show the probability plot state linear, therefore approximately normal. You have to include that, or you can draw a box and whisker plot. Now, please keep in mind though, with a box and whisker plot, you never, ever, ever state that a box and whisker plot is approximately normally distributed. You only state that there's no strong skewness or outliers in the box and whisker plot. So if there's no strong skewness or outliers, then that's pretty much going to be able to tell us that it's approximately normal. Okay, but you would have to state no strong skewness or outliers, therefore we can state that the t-distribution is approximately normal. Okay, so notice the conditions were the same as proportions and means. They were the same as the proportions except for the normal conditions. So how will you lose credit on the AP exam for the normal condition? If the central limit theorem doesn't apply and you state that it does, you will lose credit. Or if the population is not normally distributed, you have to include a graph of the sample data. So if the central limit theorem doesn't apply and the population is not normally distributed, then you have to show either the normal probability plot to show that the sample is approximately normally distributed, or you have to show the box and whisker plot. Okay. Also make sure that you understand that you don't understand the condition is about the population. So this condition right here, okay, is sort of based on our population. So what should we do if the normal conditions aren't met? So if the normal conditions aren't met, all you're going to do is state that the condition isn't met and you're going to proceed with caution. So that's basically telling people, all right, we have a condition that's maybe not exactly correct, but we're still going to keep going. Can you use your calculator for the do step? Absolutely you can. You can even do it on the free response. Just make sure you show all of your work, your state plan, do conclude, and your numbers plugged into the confidence interval. All right, now if the normal conditions aren't met, why can we still proceed with caution? So how is it still going to work? The t-distribution is robust. All right, well, what exactly does that mean? Robust means that the actual capture rate, even when the assumptions are violated, will still be close to the actual capture rate. Okay, that sounds a little bit confusing. So what that means is there's more area in the tails of the t-distribution. All right, so since there's more area in the tails, it's still going to capture most of the curve. All right, so there's a lot of area in the tails, so when I use that t-distribution, it's still going to capture the true mean, true proportion, true mean 95, 90, 80, whatever percent of the time. So on the AP exam, you won't be asked to construct a confidence interval if a condition is clearly violated. There's no accepted rule, so if you do a box and whisker plot, there's no accepted rule for identifying strong skewness or outliers. In most examples, if it's moderately skewed, it's probably okay. If there's a major problem, the graph will be majorly skewed and you don't know what to do, just make sure you state proceed with caution, so you're sort of protecting yourself. Okay, so we'll go over this in the next video.